All right, so this is the chapter 1 of this particular uh, course. Although it's not the chapter 1 in the book is chapter 15, but considering the AC circuits and sinusoidal steady state analysis, this is chapter 1. We will have sort of a review of all the topics that we covered during circuit theory, the part 1 of this course, which is the prerequisite. So it's a good review for everyone who wants to get a review from circuit theory. As you can see, that basic approach, nodal analysis, mesh analysis, superposition theorem, source transformation, and Thevenin and Norton circuits and phasor diagrams will be discussed in this session. And once again, it's a good review for all those who want to get a refresher for circuit theory. So the basic approach for network analysis in this particular course, how to analyze AC circuits, we will use all the theorems from circuit theory. We will use node analysis, mesh analysis, and everything. But the problem that we have to add is that we transform the circuit to phasor or frequency domain. And we have learned a bit in the previous tutorial. Then we solve using all the basic things. This is all that we have learned from circuit theory, then transform back the result to phasor or time domain. So it's just like this, time to frequency, then solve the variables in frequency and frequency back to time. So it's like the things that were difficult in time domain, as we have seen in the tutorial, the things that are difficult in time domain, we will add another step to make those difficult things simpler, and then we go back to time domain. It's as simple as that. All right, nodal analysis, just a review, that we select a node as the reference node. Take the highlighter, no, laser pointer. We select the node as reference node, which is normally the ground. Then assign voltages V1, V2 to whatever it is to the remaining nodes. The voltages are referenced with respect to the reference node. Apply KCL to each of the nodes. Use Ohm's law to express the branch currents in terms of node voltages. Solve the resulting simultaneous equations to obtain the unknown node voltage. This is standard procedure, and we can do the details while doing the circuits. Anyone has like any confusion about these particular steps? This is, I think, the
no sir, no sir.
Yeah. All right. So let's proceed with considering this circuit. We have this basic circuit. I'm calling it basic because there's just one source. We have a sinusoidal source of 20 cosine 4t, a resistor, a capacitor, an inductor, a controlled current source, controlled current source, and an inductance, right? So we will solve this circuit using nodal analysis. Sometimes in the question they mention that you use nodal analysis or mesh analysis. If it is mentioning, then you have to use that particular method. Otherwise, you're free to use any method to solve any circuit. You have to find this Ix for this particular circuit. Okay. If it wasn't for this inductor or capacitor or this sinusoidal source, I think it's a very easy circuit. But since we have frequency and we have the passive elements, the inductor and the capacitor, we have to use techniques that will make this circuit easier to solve in terms of the basic approach. Once again, remember, in resistive circuits, we just have the real values, but now we have the frequency, then we'll have phasors. This means we'll be using complex numbers. Once again, a reminder for those who do not have a calculator that can solve complex calculations, it's a good time to invest in a good complex calculator. All right, so let's do this circuit. I'm using my pen here. So we can see that there's this node V1 and V2, and there's a control source which depending upon this particular current. So what we have done here is first of all converting the circuit into frequency domain. So if you look at this one and this one and this one, we have to convert this into frequency domain. If someone can remind me what is the value of omega. What is the value of omega and where do we get it from?
4.
You can maybe
4.
type in it 4, very good, 4 radian per second. Okay, this is coming from this particular value. This means the inductance and the capacitance, we can convert them into frequency domain as well. If you remember, XL is J omega L, which will be J times 4 times 1, which is J4, and XC will be equal to 1 upon J omega C, which is 1 upon J times 4 times 0.1, or 1 upon J 0.4. Is that clear? Oh, there's one more inductance as well. So this is J omega L1, and this is another one. So XL2 equal J omega L2 J times 4 times 0.5 will be J2. All of them will be in ohms. All right, and this source will be transformed into 20. Since remember, the cosine is our reference, so we don't have to convert from sine to cosine. We will keep it like this. The phase for this particular source is 0, so 20 angle 0 is the source volts. Right? So let's proceed. What I'm trying to do is to put them in a way that once I'm solving everything, I put them in the actual type form as well. So just to go back, this is our calculation. Omega is 4, XL1 is J4, XL2 is J2, and XC is 1 upon J.4. So if I move forward, all of the values are here. This J, 1 upon J omega C, when we simplify it, 1 upon J.4 will be, the J will be negative J, and 0.4 is 2.5 ohms. All right. Now we can consider each one of them, J4 and minus J2.5 and J2 ohm, as if they were resistances. You can see the ohm sign there, ohm sign there, and ohm sign there, impedances or resistance. Now we can write the equations as we used to do in circuit theory. So I am sure that you would agree if I write the equation at V1 or at V2 will be, if I take V1 will be V1, normally I take the currents away from the node, but since there is mentioned this arrow here, so it will be this source minus V1 upon 10, then V1 upon minus J2.5 and V1 minus V2 upon J4. Go next. So normally I write V1 minus, so V1 at, I think I have this thing, nothing. Okay, at V1 minus 20, you can see that this is 20 angle 0 upon 10 plus V1 upon minus J 2.5 plus V2, the undo sign, eraser. V1 minus V2 upon J4 equal to 0. All right. Similarly, at V2 at this particular node will be V2 minus V1 upon J4 for this inductor minus 2Ix and plus V2 upon J2 equal to 0. Okay, for my grading and assessments, these two are the equations that I will be inspecting in detail. All right, I want to see these equations because this is what network analysis starts with. You have to model the circuit in terms of mathematical equations. These two are the most important step. If we have a 10-mark question, once again, I will be grading 5 out of 10 just based on these two equations. Okay, I cannot move forward for some reason. No, now it's coming. So this was actually at node 1 and node 2, and eventually we get
Sir.
yes.
Sir, at V2 there, is it not V2 minus V1 over J4 plus 2Ix, sir? Since both of them are converging at the junction together.
Okay. Once again, if I let me draw it again. Okay, J2 and J4. What I take it as convention is all the currents are going away. So this is going away and this is going away unless there is already specified. Like this one is going towards. And according to KCL, all the currents going towards the node are negative and all the currents going away from the node are positive. So I'm considering this current as V1 minus V2 away, V1 minus 0 away, and this is towards. So V1 minus V2 away is positive, but this is going towards, so negative, and V1 minus, so this is positive. Is that clear?
Oh, okay, sir.
Yeah. So you might be confused by this particular arrow maybe. So if we consider this arrow, this one, then we take V1 minus V2 upon J4, which eventually will turn into negative sign. All right?
Right, sir.
For some reason, I cannot move forward. How do I? Okay. I cannot move forward for some reason. Okay. Keep. So we are at this particular one. So we have two equations. All right. Let me go back to the screen again. Okay. Okay. Node 1, node 2. Okay. So this is what I'm doing is at the end of the scribbing that I'm doing, I'm keeping the actual solution here in typed form as well. So if you consider your particular concern, you see that this is on this side. So we are taking this arrow as, so it doesn't matter. We eventually get the same result. All right. If you go back, you can see there is Ix in this particular equation. So one thing that I missed was Ix. Ix is coming from this branch. So Ix is equal to V1 upon minus J 2.5, which we can replace in here, which we can see in the next slide. Again, I'm having this problem. Next slide. Next. Not able to go. Sure. For some reason, I'm not sure. keep, and let me go to this one. It's my Wi-Fi, okay. That's okay. Not sure. Don't know what to do. Okay, let's go with this. So we have first equation here, simplified form. Okay, how many of you have problem in solving complex numbers? Because my main concern is about writing the equations, manipulating them, but not on solution, because I'm not teaching complex numbers here. My main concern is to teach you how to solve circuits, not doing the mathematical calculations. If anyone has a problem, we can have a separate session, separate tutorials, just to solve complex numbers. So if anyone has any concern about solving the numbers, please let me know right now, maybe, so that I can plan my lecture accordingly. You can do complex calculations. Like if I ask you how we come up from this equation to this equation, is that okay with everyone? I'm waiting. Okay. Nazir, you're okay or you're not okay? I'm sorry, I didn't. Are you okay with the complex calculations? Go to chat. Okay, sir. Okay, good. Thank you. All right. So anyways, if anyone has, I raised my hand. I didn't raise my hand. Somehow, I don't know. Okay, so we simplify this equation to get this equation, and at node 2 we found out that we had this equation, and we substitute Ix equal V1 upon minus J2.5 in this equation to get this. Simplify, we get this equation. So we have one equation here. We have one equation here and one equation as this one. Okay. Let me proceed if I can. Okay, good. So we have this equation, equation 1 and equation 2, and in matrix form. This shouldn't have appeared right now because I wanted to show you, but anyways, in matrix form, I want to put these numbers in matrix would be 1 plus J 1.5, J 2.5, 11, 15, V1, V2 equal 20 and 0. So I hope that this is also standard for everyone. Okay, we are using the matrix form to solve these equations, but you can use any method. If you want to use the elimination or simplification or solving simultaneous equation, you are more than welcome to do that. Once again, I am not right now focusing on teaching you how to solve equations. I'm teaching you how to represent a circuit in equations and then get the solution. The way you get the solution is totally up to you. You can use any method from calculators or whatever. And if we want to solve it using, let's say for using Cramer's rule, if you remember, we want to find the determinant and then delta 1 and delta 2. Determinant is simply 1 plus j 1.5, j 2.5, 11, and 15. And just a minute. It's like my system is becoming a bit slow. And this comes up to be, when we simplify it in terms of determinant, we use this times this minus this. So we get 15 minus j 5. If it's delta 2, for example, delta 2, we replace the second of the column, because which is representing to V2, with these numbers. So delta 2 will be 1 plus j 1.5 and 11, and we bring these numbers 20 and 0, and then we simplify, we get something. And then similarly, if you're talking about delta 1, will be 20, 0, j 2.5 and 15. Sorry. Oh, this is okay actually. And we find these values. Okay. By the way, delta 1 is 220. I have it in my other slide open here. All right. Anyone has any concern? I have to go a bit slow in the beginning so that everyone can follow. All right. Again. Okay. So this is the determinant delta, then delta 1. Once we have delta 2 and delta 1, we can find V1 as delta 1 upon delta. This is called Cramer's rule, if you remember. Cramer's rule. And we get V1 as 18.97 and V2 as 13.91 with the particular angles. Right? Once again, I'm trying to focus more on how to write the equations and not how to solve it. But if anyone has a problem, please don't hesitate to ask that how did we get this step. Just to do recall, we put these equations in matrix form, then we found the determinant of this thing as in here. We come out to be like this. Delta 1, we keep the delta, but we replace V1 with 20 and 0. Delta 2, we keep the first column same and replace the second column with 20 and 0. We solve it. We want to find V1. V1 is delta 1 upon delta. V2 is delta 2 upon delta. Solution that depends on your calculation capabilities. All right. Okay, we have solved the equation. Okay, most of the time, this is my experience with circuit theory. They will be very happy to find this and put them in a big block and say, okay, this is my answer, like this big answer, very happily. But this was not the question. Don't forget that the question was find Ix. Okay, don't forget that the question was to find Ix, this current. Okay, so once we have V1, remember Ix is V1 upon minus J 2.5, and we just put V1 value here, J 2.5 negative, and once we have, this is in phasor domain, by the way, we convert this back into time domain. So remember that this will be the amplitude. We already have the frequency, and this will become the phase of the signal. All right. So this is very much standard like nodal analysis, nothing new. The theory and concept wise is all the same, except we are working in complex numbers, right? Okay, so again having this problem. Okay, now if we consider this as an exercise, we will be doing examples and exercises. Exercises automatically converts into your homeworks that some of them will be doing in tutorials and some of them as, so consider this as an exercise that you have to do it by hand as a homework or as a tutorial. Right now, we consider this as tutorial problem, okay? But from now, like from later on, we will consider them as our homeworks. Just to give you the highlight of the question, it is very much the same. It's in cosine, the frequency is 2. We have 2 nodes. This time we have a voltage controlled voltage source, pretty much standard. We have 2 nodes, right? I think this would be a piece of cake for you guys, hopefully, inshallah. Anyone has a question about this particular question, this exercise? Raise your hand, 10 seconds. All right. Okay, may I get a raise of hand for those who are following actually? Thank you. Thank you. Thank you very much. Now we have 32 students. Okay. All right, let's move forward. Another question. Example 2. We have another question. Can someone pick up something from this particular question? Anything particular about this question that's a bit new from the previous 2 questions?
Supernodes, sir.
Wonderful. We can see that V1 and V2. So if I just remove this, if I just remove this part from this thing, it's a standard question, just like the first one. Very easy. But this particular thing makes it a bit difficult when we start writing the equations. Okay. When I say I'm more concerned about how you are solving the circuit and how you write the equations, I mean that, for example, a common mistake that I have seen is if I write the equation, okay, so I'm doing a wrong thing right now. Please do not take it as a solution. So minus 3 angle 0 at V1. Minus 3 angle 0 this current, and plus V1 upon minus J3 plus V1 minus V2 upon 4 plus V1 minus V2 upon 10 angle 45. You see the mistake? This is not an impedance. Once again, this is not an impedance. This is a source. We remember we're writing the current. This is a current. This is a current. This is a current. This is not a current. This is voltage upon voltage. This is not a current. This means this is the basic mistake that you're making, and if you write this equation, this is where I will penalize you, that you're writing a wrong equation. You have a problem in your understanding. All right. So make sure that you don't do this mistake. Erase all ink on slide because. Okay. So how do we do it? What is the supernode? Just a refresher. Nodal analysis with voltage source. So a supernode is formed by enclosing a dependent or independent voltage source connected between 2 non-reference nodes and any elements connected in parallel with it. We analyze the circuit with supernodes using the same 3 steps mentioned above, like the previous steps, except that supernodes are treated differently. So in short, whenever we have 2 nodes and we have a source in between these 2 nodes, very nice drawing. we have two nodes, and in between them we have a voltage source. Then we cannot proceed under normal nodal analysis, but we will be treating this particular node as a super node, and we treat it differently. So what are the steps? Take off all the voltage sources in super node. Okay. Apply KCL to supernode. So we consider the supernode as the node. If I go back, we will consider this as a node. Okay. And we should have also ignored this one, but even if we keep it, it doesn't matter. But anyways, whatever is connected between these two will be considered as a, so this is a node now. Okay. This is my coloring exam. Okay, so will be like V1, this current going here, and this current branch, this branch current, and this branch current. So minus 3 angle 0 plus V1 upon minus J3 plus V2, because it's here is V2. I have just colored there's V2 here, V2 upon J6 and V2 upon 12 equal to 0. I'll do this in detail in the next slide, but just to show it with this very nice coloring thing, let me remove it. All right, so how this was the basic circuit, and we removed everything that was between V1 and V2. We go back. This was the basic circuit, where there is a voltage source here between V1 and V2. We remove everything that is between V1 and V2, everything. So we remove this, we remove this, right? And we consider this as supernode. Nodes 1 and 2 form a supernode. Applying KCL at the supernode gives, so I just wrote the equation, we will get this particular equation. So 3 V1 minus V1 upon minus J3 for the capacitor, V2 upon J6 for this inductor, and V2 upon 12 for this, and this is also the current source. Normally I take it towards the node, it was supposed to be actually here, but I bring it on this side. So, and simplifying it, we get an equation. So this is one equation. Okay, people might think that the topic nodal analysis was first and then there was supernode, so that makes things a bit complicated. Actually not, that simplifies it. Simplifies it because one equation is already there. Which one is it? Again, why? So this is the equation from the supernode. Let me go back. We know that this is V1 and this is V2, and you know these are potentials, potential differences. The good thing is we have the potential difference available between these two. So I can say if this is positive and this is negative, I can write V1 minus V2 equal 10 angle 45 degrees. Is it okay? So we have a very simple equation. Rather than having to consider the J's and all the components, we get one very simple equation from supernode, or V1 equal V2 plus 10 angle 45. So let me go to, where is the, this one. We get V1 equal V2 plus 10 angle 45, and using this V1, so now we have the value of V1 directly. We don't have to solve V1 like sort of elimination, I think. We already have the value V1 equal V2 plus 10 angle 45. We can place this V1 here. We get thank you. This is nice. I say hello, Falan. Falan, say hello. Hello. Thank you very much. All right. So we replace the value of V1 from here and we place it in this equation. We get this equation, we solve it, we get V2 equal 31.41 angle minus 16.18. All right, any question, guys? Let me just go through the steps again. We have this circuit in which some things are gone from here. Let me remove all the ink. We have this circuit in which there was a voltage source between two nodes, V1 and V2. We consider this as a supernode. We write the equation on the supernode. So this current and this one and this one and this one, we get the equation, and then one equation we get from the supernode itself, which is from this thing, which is V1 minus V2 equal 10 angle 45, and we have two equations and two unknowns. We can proceed to solve the circuit. Right. Oh, that's why there were lines. And once we have V2, we can place the V2 in this equation to find V1. So V1 is 25.78. So we have found the values. All right. Any question?
No.
Any question, anyone? Okay. I am stopping the recording for this topic, giving you 5 minutes, just 5 minutes too much, just 3 minutes to go through the concept again. I'm still here. Let me stop the recording. I'll start the recording for the next topic in the next session.